Theorem point 2 is on the existence of the Laplace transform. So let's go over that. If f is piecewise continuous on 0, infinity, and has exponential order alpha, then the Laplace transform exists for for s greater than alpha. So let's go over the proof of that. So first, when you do a proof, you have to assume this hypothesis all the way to there. So this f is piecewise continuous and has exponential order alpha. Okay, then we want to prove it exists. So basically the integral exists. Okay, so let's assume f of t is piecewise continuous on the on the including 0 approaching infinity and has exponential order alpha. We will show that the Laplace transform of f of t of s, which is the integral from 0 to infinity, e to the negative st f of t dt, converges, meaning like it exists, like the limit converges, for s greater than alpha. So first, let's break up the integral. So we're going to take the integral of the Laplace transform. I'm going to label this star because we're going to use that later. So the integral is 0 to infinity, e to the negative st f of t dt. And we're going to basically break this up once. We're going to say this goes from 0 to t, e to the negative st f of t dt, and then we're going basically, we're going to stop at t, and we're going to add it to, and then we're going to say t to infinity. This just helps us navigate what's going on. E to the negative st f of t dt, where t is chosen such that the absolute value of f of t is less than or equal to m e to the alpha t. So remember, when you have exponential order, you are just saying that eventually f of t is less than or equal to the exponential. So it can do, stuff like this, but the exponential eventually goes like this. And so we got to find that. We're saying there exists some value t. That's defined by the exponential order. So we have to break it up to allow us to do that. Okay, so let's continue. All right, so chosen such that it is true. All right, so the first integral exists. So the first integral, so this exists because it's finite, and this is f is piecewise continuous, so this is piecewise continuous, so a piecewise continuous function is integrable, or has an antiderivative, so, or the limit exists of the integral. So let's write that up. So the first integral exists since f is piecewise continuous, and that means, so, and thus e to the negative st f of t is also piecewise continuous. on 0 to t. Okay, so that we know that. So for the second part, we're going to use the comparison test for integrals. So for the second, so when I say the second part, I mean this. So the second part, we will use the comparison test for integrals. So basically, we're going to look at f. We're going to use the fact that f has exponential order. So since, so just briefly, basically, if you can show at some point, this is just, I'm going to erase this after I'm done here, but the comparison test for integrals basically says, simply speaking, if you have like h of t is always less than or equal to g of t for all t in some interval, then so are their integrals. I mean, that's essentially what you're doing. So since you'll have exponential order, that's what we're going to show. So it's we're going to use essentially this exponential order concept and then be able to apply this to it. Okay, and then we want to put in the details though this time. Okay. So since f of t is of exponential order alpha, for t greater than or equal to capital T, we have absolute value of f of t is less than or equal to m e to the alpha t. And so we get this equality and integral. So we have then that absolute value of e to the negative st f of t. So now we're going to look at this. This integrand right here is what we're saying. So this is we're starting here because it's a true statement, and then we're going to use this fact in this inequality. So you don't need absolute values around e because it's always positive. Okay, now we're going to use the fact that we have above, that is less than or equal to e to the negative st. So that's just recopying the same thing on both sides that's positive. So that's less than or equal to m e to the alpha t by that assumption. So that's equal to m e to the negative st plus alpha t. Let me simplify that a bit. That's e to the alpha minus s times t. I like to write it like that first. I think the book's a little different. Doesn't matter though. Okay. And so we're going to write this, I'll write just like the book now. So that's m e to the negative s minus alpha t, and that's true for all t greater than capital T. So now essentially we show that converges. So we're going to show that you can take the integral of this and it converges, or not that one, this one, when s is, where's our hypothesis again? When s is greater than alpha. So let's see that. Okay, so we have the integral from t to infinity m e to the negative s minus alpha t dt. So we're integrating essentially the right-hand side. If we integrate both sides, then that's essentially what you're able to show, and that it exists. So if the right-hand side exists, then the integral exists that we're after. So that's equal to, we can factor out the m. So now you just go through this simplification a bit, and then you get negative s minus alpha t dt. Okay, so that's m, and now we take the limit as n approaches infinity. T to n, e to the alpha minus st. The rest of this kind of falls out when you just take the limit. So that's m, and then oops, put that in the wrong spot. It's m times the limit. So now take the integral of that, and what do you get? Okay, when you take the integral, you get e to the alpha minus st all over alpha minus s, right? You just divide by that. And we evaluate that from t to n. So we continue to simplify. We can factor out the alpha minus s, and then that's just the limit as n approaches infinity of e to the alpha minus s times n minus e to the alpha minus s t. All right, and then we have for alpha less than s or s greater than alpha, this whole thing is negative. So you want this to be negative. In other words, s is greater than alpha, right? That's what we want. And so this whole thing will go to 0 when you take the limit, and this will be fixed. So you get then, so take the limit, and you're going to get this goes to 0, okay, because of that assumption. So after you take the limit, you get this equal to m over alpha minus s, negative e to the alpha minus t of t, which is equal to, and then we just change the order in the denominator. We get m, so it actually equals m alpha minus s times t over s minus alpha. And that's a real number. So that exists. So that's in the reals. So the integral exists, therefore converges for s greater than alpha. Since both integrals converge, the Laplace transform exists for s greater than alpha. All right, so since both integrals of this above here, right, converge. So we're talking this one converges and this one converges. That is the Laplace transform. So we got it. Okay, so it converges. And therefore, the Laplace transform of f of t of s exists for s greater than alpha. Okay. All right, so that's a nice proof I wanted to go through so that you can see how it's done. So another existence theorem for some of these definitions. Next, we go on to 7.3,